waiting for more people. Okay, he's coming, yeah, that's, and then we can rewrap for him.
I can for a minute, but feel free to start without me. He said you can start without him.
Oh, nice of him. Thank you.
Will you tell us some rules?
Yeah, and in fact, I think I decided to follow your suggestion of yesterday and put it into as much context as I have time today. So, I prepared, yeah. Surprisingly, and nobody would believe me, but sometimes I do prepare. I hope this is not yet recording. So, all you see is a lot of color pens also, that's good. Any questions? So let's wait for from Jakob. Any questions from your side before we start? It's usually a bad sign if there are no questions. I could, but this is not actually related to what we are doing today. You do this, and also for Clem. So while he's leaving, so what we proved yesterday was try to give you the idea of how to find good starting points for Newton's method, this grid, using some nice properties of conformal geometry, by holomorphic geometry. Oh, you disappeared the second half, yes. Yeah, maybe so talk to the TA, and then we can review this. Is that okay? I have some pictures and some notes. Hey, good.
So have you proven yesterday that number of channels to infinity corresponds to the number of subsecond geometry?
Yes, in the immediate basin. And that is something I can quickly review and hope that Jakob comes back. Not yet official part of the class. So you have the immediate basin, like so. You have the Riemann map to the disk, sending the root to the origin. And then this is a proper self-map of some degree m. Here the Newton map has degree d, number of roots in general. But the self-map from the immediate basin to itself has a degree which is possibly smaller. And then that means every point in the Riemann sphere is d pre-images. I'll just review quickly of yesterday before we start. Every point in the Riemann sphere has d pre-images, m of which are in the immediate basin, and then the rest are somewhere around. Okay, so here you have a proper self-map of the disk to itself of degree m, and m is at least 2. Because in general, you have a super-attracting fixed point, which introduces degree 2. And if you have such a thing, then on the boundary, in fact, you can, by Schwarz reflection or whatever, this map F, you can extend it to the whole Riemann sphere. You know Schwarz reflection? So it's a rational map on the Riemann sphere of degree m, and it restricts to a self-map of that degree m on the circle. And that means you have m minus 1 fixed points here on the circle. So the degree is m, you have m minus 1 fixed points on the boundary of the immediate basin. And you asked what could be the possible boundary points here. Well, infinity here. Each of those is a different boundary fixed point on this model. So the number of accesses to infinity is 1 less than the degree. The degree, if you have a proper self-map of degree whatever, the number of critical points is 1 less than that. And now 1 critical point is already is the root. And then the others must be 3 critical points of the map here, which are 3 critical points. Get the idea? Okay, but that was the thing that you were still there when we discussed this. Okay, so That was a review of last time. So welcome everybody to, sad to say, the last session on holomorphic dynamics and root finding here at KSE. And today, well, we talked quite a bit about root finding in various contexts. Yesterday we discussed geometric properties of Newton's method. Today, but holomorphic dynamics is a lot bigger than root finding. I'd like to discuss a bit about the Mandelbrot set and some combinatorial properties. Let's see how far we get in the end to open questions and how you actually prove things in the Mandelbrot set. So the first thing I want to prove is the theorem which we mentioned before, that the filled Julia set of some polynomial, filled Julia set, is connected. So the filled Julia set is the set of all points in the complex plane that have bounded orbits, so they do not go off to infinity. If and only if it contains all critical points of the polynomial. Infinity may be a critical point which ignore, and all the others must be in there. Then, and only then, this is a sharp condition. This is a sharp condition, then and only then is the Julia set connected. And as a corollary, the set of polynomials so that KC is connected. This, I was told, one should discard. Let's hope one remains. After all, KC is connected. So that's the kind of conceptual definition of the Mandelbrot set. It's the same as this of parameter C, so that the sequence z0 equals 0, zn plus 1 equals zn squared plus c. The sequence is bounded. Bounded means it's in the filled Julia set, and this is the critical point. Okay. People look puzzled.
Because the only critical point is 0.
Yes. Right? So that's what we need for the two. This is the conceptual definition of the Mandelbrot set. This is the computational definition. And they're the same. And I would like to prove one direction is a bit easier than the other. So let me prove at least one direction. So if the filled Julia set is connected, so here's some sort of filled Julia set. And the connected means that the complement is simply connected. So that means Riemann sphere minus the filled Julia set is biholomorphic to the complement of the closed disk. Right? So suppose that's the case. Then we take the Riemann map from the complement to the complement here. And here in the complement, we have the polynomial P. That means we get some biholomorphic map from here, which sends this domain biholomorphically to the escaping set. Then there is a degree D self-map, proper degree D self-map, and we send it back here. So we have a map F, which is phi inverse then P then phi. This is a map from the complement of the closed disk to itself. And F of infinity is infinity. Right? And if you check this, here we have degree D. Then this essentially applies that f of z equals z to the d. up to, there could be a coefficient in front, but by scaling, multiplying phi with a coefficient, you can get rid of that. So there's essentially no choice. And it wouldn't matter if there was. So that means you have an interesting dynamical system. Here you have a simple dynamical system. And everything you want to understand here, you can check here, up to bi-holomorphic coordinate changes. So where does z to the d have its critical points? At 0 and at infinity. There is no critical point here. Therefore, there is no critical point there. All finite critical points of P have bounded orbits.
So we need that infinity goes to infinity.
Yes. Okay. So that's the easy direction. For the other direction, you have to work a little bit, but it's also conceptually interesting. But at least you see where it's coming from. It's not a coincidence. So then let's talk about local fixed point theory. What we know about this polynomial is infinity is a fixed point. And it's a critical point also of maximal criticality. So rather than looking at infinity, we conjugate by 1 over z, and then we have another map, well, G is a bit better perhaps. Here is a neighborhood of 0, and G sends 0 to 0, and G of z equals z to the d times 1 plus higher order term, something like this.
Where does u come from?
I just take a conjugation in a neighbor of infinity. So I know I take a polynomial. So if it's well, we know this. Now suppose we have an arbitrary polynomial, and I want to show the equivalence of these two conditions. And what I know about the arbitrary polynomial, infinity is a fixed point, and locally at infinity it has the form here near infinity, p of z equals z to the d times 1 plus, and here it's lower order terms at infinity. And if you take 1 over z conjugation, z to the d at infinity is z to the d at 0, and the lower order terms become higher order terms. And now one thing you need to check is, not too hard, local fixed point theory. You have a fixed point out of a holomorphic map, and then you want to show it is conformally conjugate to the first interesting term of its Taylor series. So there's another biholomorphic conjugation to a map h of z equals z to the d. I will not do it, but it's a bit tedious. So the way you prove it, you take some point, so you want to define the map C. The closer you get to the origin, the better this map is approximated by z to the in the first place. So there's always in these cases, you have a scattering argument, you take some point where you want to evaluate it, take n points in the dynamics until you're close to 0, take the image here, and then take n points on the backwards orbit. And when n is larger and larger, then the approximation will be ever better. So something Cn equals of z. You have z, you take, what was the thing here? Gn iterates. And then you take n backwards iterates here. And then you hope that Cn tends to C infinity, which is the right thing. That's a frequent argument, and usually it works. Except there's a little problem, H is not invertible. You have to get around that problem. And you can, but I don't want to get into it too much. But in any case, locally, you show that any super attracting fixed point is conformally conjugate to the simple map Z to the D for the same power, depending on what degree of the critical point you have. You don't want to slice the plane, you want to have something in the neighborhood. Right, but you don't want to use that argument. You want to work on a whole neighborhood. But it's a bit trickier, but easier at the same time. When you have the map here is D to 1, so when you take the inverse, it's 1 to D. So you kind of match the 2 degree D forward and 1 over D backwards and get a limit anyway.
Maybe it's easier to work with the Riemann surface that corresponds to the D.
So what you really, let me give you the idea. In one step, you have something, let me write G over Z is Z to the D 1 plus higher order terms. Now we want to take a dth root of this, right, which is the inverse by H. Taking the dth root of this, dth root of Z to the D, that's easy, is Z. And dth root of 1 plus something small, you choose the branch that's near the 1. And that trick works for all the iterates. So there's an ambiguity in the dth root, but if the argument was the dth power in the first place, you can deal with it. Okay? So that is roughly speaking a proof. I mean, you're old enough for your own epsilons and deltas. And section 3 of my book might help you. But that's the idea how you locally can deal with super attracting fixed points. Are you okay? So now let's try to promote it from locally to more globally. And maybe, well, I erase this bit. So here is infinity for the polynomial. Somewhere, if you wish, there's a Riemann sphere, here's the point at infinity. We have a neighborhood around infinity, and then we have another Riemann sphere with infinity. And here we have the polynomial Z to the D, which is H of Z. So we have near infinity a biholomorphic map. There is infinity. If you wish, it's the north pole on the Riemann sphere, yes. So you put them somewhere here is the base, but just for the Riemann sphere, it's just one point like any others. If you don't like it, take 1 over Z coordinates. Yes, you should like it, but now it's really good to work on the at infinity. So here we have this biholomorphic map, phi, near infinity. And, well, the points drift to infinity for both maps. The Phil Julia said, for now is rather far away, and here's the closed disk. So we have this map here. Now there is a set, and somehow here you have circles that map to ever smaller circles around infinity. Right? And that means here you get some sort of circles around infinity also. So this is the last annulus on which the map was defined. Now we take all the points which in one iteration hop here. So that means there is another annulus. Map one step forward, go to this one, take these roots, and by the trick which I just erased, you can keep extending it further and further. Okay. You can extend it, in fact, annulus by annulus. And there are two possibilities. Either you can extend it indefinitely, and then you get smaller and smaller neighborhoods around the filled Julia sets. And then you have the biholomorphic map from the complement of the Julia set to the complement of the disk. And you're in this situation. That means the filled Julia set is connected, and there is no critical point. You can always try the same argument, but at some point it may be that the polynomial has a critical point which goes here. And then you're in trouble. Then there's a local, you want to extend it here, the image is there. The forward map locally is already not invertible. And then the argument breaks down. So, therefore, if you look at this carefully, you can keep taking pre-images for these things, annulus by annulus, until possibly you ever hit a critical point. A critical value is okay, but pre-image of critical value, the critical point is not okay. Okay. And in fact, then what happens is, so that was near infinity, and somehow in the finite complex plane, what will happen is you have a critical point. There is a critical value through which you still have a circle here. But the pre-image of this circle, you have, well, let me first draw it. The pre-image will look like this. You take circle after circle, suppose the critical value is here, then the circle has two directions in which it continues. When you take a pre-image by a critical point, the local degree is 2 or higher. That means these two directions, here and here, have pre-images that are 4 or 6 or something, which is not a circle. And then part of the Julia set is here, part of it is here, and it's already disconnected. You see that? So that's pretty much the proof. You see this argument.
So you said that we have a biholomorphic map phi, right?
Mm-hmm.
And it is such map that our it conjugates our dynamical system to be c to the power d, but and it also takes the set to this. Well, to neighborhood.
You start with some neighborhood on which you have some kind of local argument, and then you keep taking pre-images.
But for each player of the sets, we have essentially one biholomorphic function, right?
Until we get to a level like so, when there's a critical point.
Yeah, but,
I mean, here in the image, we always taking pre-images, we keep getting annuli until we reach. We never reach, but we eventually fill the complement of the disk.
I wonder how do we at the same time get both the phi goes to this values go to some disks, some circles, and that it conjugates to z to the power. We first conjugate it so that it's z to the power d, and then.
The first step is just a local conjugation in some neighborhood. And that was the kind of argument we were discussing here. So here you have exact circles that map to circles closer to infinity. This circle structure you transport back by phi. Whatever it is, these are not geometric circles, but pre-images of those circles under the biholomorphic map.
So we first construct the biholomorphic mapping and
near infinity.
Then we construct the circles and then we map them and then okay.
Yes, you see, here I try to draw proper circles in perspective And this looks more funny.
So this is a procedure to fill in this complement of the Julia set by these circles on this usual agreements here. And we take this filling by the dynamic itself, so to say. And like
it's a very dynamical construction, yes.
Yeah, and so by this construction, we get exactly those points that are not in the Julia set.
Not in the filled Julia set. Well, so any point that will escape will get after a finite number of iterations to this neighborhood, so we will recede after a finite number of steps, provided we never have a critical value of which we have to take a pre-image. So that's the only obstacle to carrying out this procedure.
This procedure avoids the critical points.
Yes. So if there are no critical points escaping, then the complement, it gets through the whole basin of infinity. And then the Julia set is connected. So that's the complement of what I had, of the easy proof before. Okay? So that's an old theorem by, we call him Böttcher, which is a German name, but somehow he was in Kazan and has a Cyrillic transliteration. So I think it's my German way of pronouncing some name, which historically was perhaps. In any case, this is more than 100 years old. Now let me skip to around 1980. So far, you're okay with that theorem? So, now let's arrive at Doherty and Hubbard. And they ask the one that what happens if it's not connected. So specifically quadratic polynomials, Doherty-Hubbard, quadratic polynomials. So we have the map, here is z squared plus c, and the map phi depends, of course, on c. Yeah, we know that, so if c is in the Mandelbrot set, then phi c from the complement of the filled Julia set to the complement of the closed disk is bi-holomorphic, that we've just discussed. But what if not? Then phi c can still be evaluated at the critical value. You see, the problem arises when we try to take a pre-image of the critical value. At the critical point, you have two values from different sides, but at the critical value, you still have nice circles. Okay? So they define a map, capital Phi, of C to be phi little c evaluated at C. And this map is well defined on the complement of the Mandelbrot set. Well, infinity, you can set infinity to infinity. Okay. And more precisely, phi sends the complement of the Mandelbrot set to the complement of the closed disk. In other words, absolute value is bigger than 1. Because you start with things near infinity and keep taking these roots. And if it's bigger than 1, taking these roots always remains bigger than 1. Okay. So we have a map from the complement of the Mandelbrot set to the complement of the closed disk. And you have to check it's holomorphic. Which is somehow, the maps phi c, you have to check this, depend holomorphically on the parameter c. And the argument, of course, is holomorphic in C also. So if you holomorphic map from this thing to this thing. Okay. I will skip some verifying details, but I hope you get the idea. And you can check that phi of c divided by c, when c goes to infinity, tends to 1. Why is that? When you're near infinity, you have z squared plus c, and you can check that, well, maybe you have to check the calculation a little bit, but especially when this c goes to infinity, well, then your map is close to z squared plus c. And it's a little calculation. It's, again, not difficult, but I don't want to get stuck in calculations. So that way, we can set phi of infinity to be equal to infinity. If you know something about removable singularities of holomorphic maps, then the map is holomorphic in a neighborhood at infinity. Yes. That means it's holomorphic in a neighborhood of infinity and continues at infinity. But the Riemann removable singularity theorem tells you that means it's already holomorphic there. Okay? So we have a holomorphic map there. The next thing to check is if C goes to the boundary of M, that means if you're close to the Mandelbrot set, it takes longer and longer until you get to infinity. That means on the backwards iteration, you take more and more pre-images. But no matter where you start, that implies that phi of C absolute values tends to 1 from above. We only talk about outside. Yes. Inside, the map is not defined. Inside, when you're in the Mandelbrot set, the map phi C itself is defined, but not where the critical point is. Here, the map is defined in the complement of the field 2 set, but if you're in the Mandelbrot set, then the critical value is not in the domain of definition of phi C. So that you can do. Okay. So, that means I have a map from some domain in the Riemann sphere to this domain, which is holomorphic, and the map is proper. One way of defining proper maps is if the arguments go to the boundary, then the images go to the boundary. It's a proper map. And every proper holomorphic map in such situations has a degree. Which are called delta. Every proper holomorphic map between domains in the Riemann sphere has a degree at least 1. That means every point has the exact same number of pre-images. And this degree turns out to be 1, because infinity has only itself as a pre-image. All the other points have finite images. And this property near infinity tells you that at infinity, the mapping degree is 1. So there's no multiplicity involved there. Exactly. So that means that phi from the complement of the Mandelbrot set to the complement of the closed disk is biholomorphic. You see that? Ruslan, can you follow? You have a holomorphic map, which has degree 1, so it's holomorphic and injective. And proper, so that must be surjective. So I'm looking at you specifically because you asked me yesterday to prove that the Mandelbrot set is connected. I think I have just proved that the Mandelbrot set is connected. That's why I was looking at you. So, if it were not connected, let me draw a wrong Mandelbrot set. Well, let me try to make it look a little bit less wrong, perhaps. So let me draw it the way Mandelbrot thought for a time. I mean, Mandelbrot said, did you think it was connected or not? In fact, he made two conjectures. One conjecture was it's connected, the other was it's not. And let me tell you, one of them was correct. So suppose it were not, then you have a biholomorphic from the complement to the complement. If it's not connected, you would get a non-contractible loop here, which would imply a non-contractible loop here, which there isn't. Well, connectivity is a topological property. So you shouldn't be surprised to see a topological proof. Stronger, yes, and we'll use that. But for now, it's a homeomorphism, which is good enough to prove M is connected. Well, we're talking about the complement, number of components in the complement. A different way of seeing that the Mandelbrot set is connected is by talking, if we erase these things. I take a family of concentric circles, like so. I have pre-images here. The map is here. If I take any circle like this, it maps to a topological circle, like so, and it surrounds some part of the plane. If I take smaller and smaller circles, I have smaller and smaller circles here. So let me call this closed domain. There's a radius r here. This let me call MR the closed domain, which is this circle and everything surrounded by it. Well, the image of this, not everything, including what's inside. It's just, I mean, the annulus, I don't know what's inside, but I know this circle maps to circle. And if I take smaller and smaller circles, I get smaller circles inside. And for every single circle, I have this closed thing here. And the fundamental thing is the Mandelbrot set is the intersection of those closed guys. Everybody that's outside of the Mandelbrot set is in the domain of definition of phi c, so it's in the image here, so it's outside of some circle. Therefore, you have this thing, and there's a nice little lemma, one of my favorite lemmas in elementary topology. The nested intersection of non-empty compact connected sets is non-empty compact and connected. So the Mandelbrot set is non-empty compact connected. Okay?
Is this map from the complement of the disk to the complement of the Mandelbrot set constructible? So I would imagine this very nice picture where we actually take these three images and draw them, like encircle the Mandelbrot set from all the sides.
It is, and I mean, we had discussed this before. I mentioned this map. You can write down its power series. And there is actually a, maybe unpublished, but a paper by our very own Masha's PhD advisor, Don Zagier, he has a paper on these coefficients, which are all rational numbers, and some of them are 0 and some not, and he looked at them. I mean, Donzaghi is an incredible person, like many others. He stared at them and produced more and more examples of which coefficients are 0. And kind of, I mean, people have done numerology on these coefficients. These are rational numbers with power of 2 in the denominator. So, it's a famous study of objective study for number theorists.
So, you find some patterns in them?
Donzaghi always finds patterns.
But I didn't know that he was Masha's advisor.
I think he was. Unfortunately, Masha, if you ever hear this, you're not registered on the genealogy page. So people cannot verify it, but you should be. Yeah. I think very much that he was.
I have a question about this equality intersection. Like, this map is not defined on the Riemann sphere. So, like, can we really use it to prove this equality?
Which map is not defined on the Riemann sphere? It's defined on the complement of the Mandelbrot set.
Yes, so like, I mean, the domain of this map doesn't see the Mandelbrot set. Like,
doesn't matter.
How can we use it to prove that it is an intersection?
Well, all I'm saying is, you take any radius, any circle of any radius, that gives us the topological, even an analytic circle there, and the Mandelbrot set is surrounded. Because outside, you go away. So that means the Mandelbrot set is contained in each of those closed sets. Right? And conversely, if you have a point outside of the Mandelbrot set, then it takes finitely many iterations until it's outside of your favorite circle. So it's itself outside of one circle. So that means you actually get equality. If you're outside of the Mandelbrot set, then you're outside of one of those circles. So the only points which remain in the intersection are the Mandelbrot set. So you only need to see the circles outside of the Mandelbrot set. And you don't need to evaluate them inside.
The Mandelbrot set is in this intersection of all of them. And if we take sample from the outside, it is not in this intersection.
Yes. And that means, often if you want to prove equality, then inclusion both ways or inequalities both ways. It's a frequent way of proving things.
So essentially the main idea is to construct this map by Holomorphic.
Yes.
And then it's much obvious.
It's one of those many trivial theorems in mathematics, but it had a nice side effect. It made Doody and Hubbard famous. So the Mandelbrot set was a big hype. And there are many stories about was it connected or not, and well, I will not get into it. And then they settled the case, and that was what made the two of them famous. Well, Doody was famous in the first place, and then Hubbard, we started work on Newton's method and played with that in France, and then so working with quadratic polynomials and dynamics, he convinced his former advisor to do this together. And then the Paris professor won that, dear Adrien Doody, you're so famous, you're working on parabolas. Quadratic, do you expect to find anything new on parabolas? If you wish, this is a theorem on parabolas. And he made them famous.
You just said that it's enough to show connectivity to just look at the image of this phi.
Yeah.
This argument with this circle doesn't give us anything new.
What do you mean, it doesn't give us anything new? It proves that the Mandelbrot set is connected. Well, I give you two. Once you have the biholomorphic map, you can proceed in two different ways. And either with the loops that I've drawn earlier, or with the circles. And maybe this is easier to make precise than the previous argument.
Like the previous one would be precise with fundamental loop, right?
I don't think we should have a competition between two nice proofs. We can have a vote who likes which proof better.
So they're just parallel.
Yeah. Okay? So, that was a request of yesterday which I thought I should answer. And then let's use it, unless somebody has different requests or suggestions. So that way, of course, I will talk here until somebody stops me, but I have to somehow watch the time. Or I shouldn't. Let's see. I still have some time. So that was item 2 of 8 of the plan of today. Let me erase something. And this biholomorphic map actually has some nice properties. Part of it we discussed earlier. What's a good blue pen? Is it this one? Better, yes. No, actually, then you have the concentric curves around it, which I draw in green, because evidently there are equipotentials for the Green function. You know Green's function in potential theory. And there are transverse curves like so, which are called external rays. And these are called equipotentials. Actually, if you know some electrostatics, we discussed that the other day. If you cut the monoid set carefully out of sheet metal and you charge it electrically, then you will get field lines and you will get equipotential lines. And this electrostatic situation, well, here there is a very simple electrostatic situation. But if you check the equations in electrostatics, they respect orthogonality. The equipotentials have to be orthogonal to the field lines. So, little check, every biholomorphic map respects electrostatic solutions. Yes, yes. So, here we obviously see a unique solution, and therefore this is the unique solution of the electrostatic problem of the monoid set. It connects with many things. But yeah, I mean, the hyperbolic density here and there, but it also connects with some everyday phenomena. For instance, if you're in here, you're very well shielded from the electric field because the field doesn't really enter the part between the components. See, if you ever get into a thunderstorm near the monoid set, this is a safe place to hide away. On the other hand, here at the end, you have a lightning rod. We can discuss at some point how a lightning rod works. But the point is that the equipotentials are getting ever more concentrated near such a thing. And therefore, the field strength, the strength of the electric field here, is the highest. And what does the lightning rod do? It's exactly that, to have a singularity in the field strength, so there is an electric field from a thunderstorm. Here the field strength is the strongest, so we'll ionize the air and break through here, and then the flash will come in this way. So therefore, anytime you build a house with a lightning rod, here's a house with a lightning, and then you build a lightning rod. You want to build it exactly very thin so that the field strength is so high. Of course, you need to have a good connection to the ground, or it will catch it and go through the house, which is what you don't want to do. But when you're here, it breaks through first here, and then it's a safe place. And if you think you're smart, I want to catch the lightning, and I make a big ball around it, so it's better visible to the lightning. It's just the opposite of what you should do. It may be counterintuitive, but this is exactly how a lightning rod works. Okay, so next time you're in a thunderstorm and you have a Mandelbrot set with you, you know what to do.
Well, where is the field the weakest?
It is, well, the weakest is, of course, if you're surrounded by electricity. So if you have something like a bus stop or so, which is from metal, that's good. I mean, field strength could come in here, but most field lines which have drawn, right, will not go more than so. So if you're in here, you're safer. And this is comparable here. You will see that the field strengths are, the potential lines stay far away from this touching point. And therefore, there isn't much field strength. It will not break through here before it is broken through somewhere else. So go to these spots.
Question, so in theory we can measure the length of those lines, and the length probably tends to infinity, right?
Remember, the boundary of the Mandelbrot set has Hausdorff dimension 2. So you want to and you cannot approximate that with the curve of finite length. The Euclidean length.
Do we know that those green lines approximate the boundary well enough to say that their length will tend to infinity?
Yes, I think that should be an easy exercise. If you had a sequence of shrinking lines like so, where the image lengths were bounded, then the geometry would be pretty easy. And I don't think you need Hausdorff dimension 2 to prove that. Something much simpler will work.
So they should approach the actual boundary, right?
Say again?
So these lines should approach.
Which lines?
So those.
The equipotentials.
Yeah.
Well, it's exactly this argument here.
Probably we can, studying this map, we can know like the asymptotics of the growth of this length.
That's very subtle. If you can do this, more power to you. People have tried.
How hard is it to find equations of something that defines those equipotentials?
Well, that's the complement, it's the uniformizing map of the Mandelbrot set. And we discussed the other day that you can compute those terms. And then you just restrict it to a circle of radius, whatever, and you evaluate it. Here it is.
And they can calculate length of that.
And of course, you can compute the area of the Mandelbrot set by integrating in the domains here.
So if you know the pattern, a closed formula for this.
Yeah, that means you have to stare at them even harder than Don Zaye did.
And this tells something.
Yeah, good luck. But of course, the whole point for all of you is to discover something that the ancient people have not. I mean, my job here was to discover things that Dewey and Hubbard had not. So just because somebody else hasn't done it, that doesn't mean you couldn't.
So those red lines, those are exactly rays from infinity to.
Conformal images of the radial lines here. This is how I define them. And let's see how far I get to more questions. So one of the famous theorems, also Dewey and Hubbard, is if you have a little Mandelbrot set period n, then there are two rays that land together at the root here of this point of period something a over 2 to the n minus 1 and b over 2 to the n minus 1. We discussed Lavor's algorithm or pinch disk model of these things. Let me see how far I get in convincing you that this is true. But that way you can, in principle, it's one way of finding where the little Mandelbrots are located. So, but that means I have to erase step 1 finally. And move to the third denomination. I mentioned this for the Mandelbrot set. For Julia sets, we didn't discuss it, but now we have to. So let me have a Julia set which is connected. Somewhere here's the critical point, somewhere there's the critical value. And let me try to draw this Julia set knowing just one thing. There is one ray from infinity at some angle theta that lands at the critical value. So I want to give you a complete topological model of the Julia set, knowing only this angle. Okay? So how do we do this? Angles, of course, every angle maps to twice the angle. And therefore, every angle has two preimages, one at angle theta over 2, and the other at angle theta over 2 plus 1/2. These two rays map to this one. And they have to land at a preimage of this point. But the critical value, every point has two preimages, except the critical value for that, the two preimages coincide. So therefore, these two rays must both land at the critical point. What happens if you double this thing? Theta plus 1. And you compute modulo 1 anyway, so it's theta, you're there.
So we don't measure in radians, right?
Always measure in full terms. The only natural measure for a compact space like this circle is length 1. Okay? Now the critical point has two preimages, one of which is here and one of which is there. And then this guy also has to have two preimages. So this is theta over 4. This is theta over 4 plus, I think it's 3/4, whatever the computation is. And there are two more which are here.
When you say here and here, what do you mean?
These are the 2 points that map to the critical point. The critical point has two preimages which are distinct. There must be two different points.
You mean that they must lie in different halves?
Yes. So this ray, these two rays map there. Therefore, all the half on the lower half will map to the complement of the ray. And the half upper part here will also map to the complement. It's a 2-to-1 map. This is symmetric with respect to z and minus z. So they have the same images. And so the image of each of the two parts is the complement of this one ray.
They like fold the sphere in half somehow.
Yes. So you connect it for the z squared plus c map, or in this case z squared plus v, the critical value. There are two critical values, v and infinity. This curve connects the two critical values, and then you can take preimages in two separate components. Okay?
So we don't know the exact location, but we know this.
We could, but we want to do topology anyway. So let me try to model this. 0 equals 1 is here. So we only know the angle theta. And then that's the only input. It has two preimages, theta over 2 and theta over 2 plus 1/2. So these 2 points must be the same. So we'll take a pinch disk again. We pinch here. And we have two separate disks, which we will this thing and that thing. Now, this point has two preimage points, which will be these two. We only know the angle. So theta over 2 has two preimages, which is theta over 4 and theta over 4 plus 1/2. And this guy also has two preimages, one of which is here, theta over 4 plus 3/4 and theta over 4 plus 1/4. I soon will forget what exactly the numbers are, but we always know there are two preimages. And now we have to connect the two preimages of this guy to the two preimages of this guy. But we cannot cross this point. So the only way to do it is to do it here and to do it there. So that means now we have 1, 2, 3, 4 disks, and these are the cut points, connection points. And then we take two preimages of this guy, one of which is here and the other which is there. We also have to take preimages of those, which is somewhere probably there and here. Of course, it depends on what angle you had, because the Julia sets will be different and the models will be different. But it's always, any point has two preimages on both sides of this diameter. And so every line has one preimage line here and one preimage line there. You keep taking the sequence of preimages. You take the closure of all leaves. You may have to fill in triangles like we had before. We'll never get a triangle out of this procedure, which are 3 rays landing here. But you may get them as limits from, we discussed that earlier. And if you take the closure, the triangle is there. And then you collapse every finite triangle, and you collapse all the other leaves, including the limit leaves. And then you have a quotient of the closed disk minus the equivalence relation. And the nice thing is that this is homeomorphic to the filtering set. In good cases. If and only it's homeomorphic, if and only if this thing, people say is locally connected. I think it's somehow, it's the right word only by coincidence, but it's mathematically correct.
And in other cases, what happens?
So you always get a map from KC to this thing here, which is always a continuous surjection. But it may fail to be injective. There may be whole. So the map is going this way, the projection. There may be some blobs here which are collapsed to a single point, which you don't see. But now we get into fields medalist Jean-Christophe Jacobs, who has proved that in many cases, Dudi and Haber proved it for many, and Jacobs proved it for many more, and then later Michal Ljubich from Kharkiv and others ever more. So this is, but it's not always true. There are cases when it's false.
It's wonderful that you can even, well, if you just take point V and then V over 2 points and 4 and 8 and so on, it's interesting that they even, the fact that they go in pairs, that in every reach, when you take another 2 endpoints, there is no region where you get like 3 points and you cannot connect them in pairs. It's not obvious at all.
Well, but the Julia set exists, so somehow it must work.
So somehow it works.
Yes. And it's easy to program. So just take any favorite angle, rational or irrational, take the preimages, and you get this lamination or the pinch disk model. So Thurston, the same Thurston that I'm talking about all the time, I should know how to spell them, it's called the lamination, dynamic invariant lamination. The Dudi has the pinch disk model. And I hope I can also talk about some work of John Milner, who was working on this also, to understand how it's going.
And you never get more than 2 points in one region after one iteration, right?
Everyone has 2 preimages, one on this side and one on that side.
So this is defined by the degree of homeomorphism.
Yeah. So it's a homeomorphism from this interval to all the way around for both of the two sides.
This is probably the way to see where we get like self-similarity.
example, we divided our disk in half, right? And then we unify those endpoints. So we sort of take each half, and then we make another disk of it, but now smaller. I don't think you need the disk model to get self-similarity. You can see it here already. But it is, I mean, any local point will, under the map, will get, the neighborhood will get larger and larger. And you see conformity, it's not only homomorphically, it's conformally that you see the self-similarity.
And you say they prove in different cases. You mean like for different, you say that it is equivalent to PC being locally connected. So
yes.
Did they prove like only partially this theorem, or like for?
No, this is true, and well, this model is always locally connected. So therefore, it can only be homeomorphic if the Julia set was locally connected in the first place. And this Julia set is defined by the parameter C. Yes.
Yes. So I mean, do you mean that they proved it for different C's or?
Yeah, for all, exactly. Yeah, I mean, this is that question depends on which point in the monopods that you have.
I wonder how those points look on monopod set if you cover what points look like Julia set.
Okay, so there are two kinds of counterexamples. One is when you're on the boundary of any hyperbolic component, there is a countable density, no, an uncountable density, topology generic, when you have Kramer points, whatever that means. They are never locally connected. That's one counterexample. And that's when this Julia set becomes very sparse, right? Yes, it has no, filled Julia set has no interior. You have, this is exactly the case when you have a periodic point that's indifferent. The multiplier is neither attracting nor repelling, nor a root of unity. And then the filled Julia set can or cannot have interior. And if it has no interior, that's the one case when it's not locally connected. Because this model will always produce legal disks, which means there's some interior, whatever that means. And the other case is more subtle. When you have a little Mandelbrot set, you have a Mandelbrot set, there's a little Mandelbrot set. In it, there are even smaller Mandelbrot sets. Within it, they're even smaller. So you have a nested sequence of little Mandelbrot sets. The big conjecture of the about the Mandelbrot set is that whenever you have such a nested sequence, it will get smaller and smaller and eventually be a point. In any case, when you're in this nested sequence, then the question is, then possibly it might not be a homomorphic model.
So, and we are interested in the limit point of those contracting Mandelbrot sets?
Contracting? What do you mean by did somebody say contracting here?
Well, they get smaller and smaller. Maybe not.
That's part of the question. So the big question about the Mandelbrot set, I gave you various versions. One version is if you take an infinite nested sequence of Mandelbrot sets in the Mandelbrot set, does it shrink to a point?
No.
Yeah, find a simple argument.
No.
And find the simple proof better before the people come up with a very complicated argument.
I mean, there should be a Mandelbrot set is closed, and we get a. Yeah, but by the diameter goes to zero. So the only non-obvious part is why diameter of Mandelbrot sets goes to zero, right?
If you say that's the only obvious parts, it is technically correct. But behind this only, a whole machinery is hiding.
I mean, so you mean like they are closed and no, the Mandelbrot set as the whole is closed.
Right, and all the subsets are closed, little Mandelbrot set, yes. And in some combinatorial sense, they are smaller and smaller. But does this mean that the diameters are shrinking? For instance, if there were an interior component in the Mandelbrot set, which is not a hyperbolic component, then by work of Yokosa, it is known that it must be an infinite intersection of ever so smaller Mandelbrot sets. But it could still contain this open set.
The diameter doesn't go to zero, right?
Presumably it does, but it's a highly non-trivial theorem.
Non-triviality is...
That's exactly the thing to show.
converges to 0, then it's just
then you're famous. I promise you, if you prove this by the end of the year, you'll get famous. Many people will admire you and some might hate you. But it's worth trying.
Is the connectedness of the interior known?
The interior is not connected. This point already disconnects these two components.
But you said that it is not known whether there are points.
Whether the vertical line here, yeah, but still the interior of the Mandelbrot set consists of finitely many components for each period, plus possibly some funny components that we don't believe in.
The question is whether there are arrays that divides every two hyperbolic components.
Okay, then we go this way. So the conjectures. One of them is MLC. The Mandelbrot set is locally connected. Oh, you know the list, yeah, okay. Another thing is that for any C different from C prime, not on the closure of the same hyperbolic component, they can be separated by a periodic parameter array. So I had a list of conjectures. So this is these two red rays separate everything above from everything below. And there are countably many such ray pairs. Can you separate any 2 points when they're not on the closure of the same hyperbolic component? Can you separate them in such a way? That's equivalent. Which is not actually hard to show. That these two things are equivalent. Well, be my guest, choose whichever of the two you can prove, and then I'll prove the other one.
So, it gives us a lot of information when you see that the complement of the Mandelbrot set is just holomorphic to a very simple region in the complex plane, but it's not enough to say something about it.
But it's still a good tool to study because these radial lines are coming from the map on the complement. And they do something. Another thing is that phi, the thing, which way do I want to go? Maybe the inverse.
Can we say that complement is holomorphic to the open disk?
Of the Mandelbrot set?
There was another 5 from complement to.
Okay.
So, if one would prove at some point the big conjecture, he would probably still use the same part of this race and this idea about
I mean, this is kind of the workhorse for working with it. And if I still have time, I was hoping I could show you something about it.
Do you need to be at this place?
We don't want to miss our own party.
Yeah, minus 1 minute.
No, I think we have. I mean, we never stop before 6. If you still want to hang on, we can still continue a little. It's hard to say. Let's continue tomorrow.
So the invitation is for 6:15
Yeah,
at this room.
they know where to find us. Okay, let me quickly, maybe with less detail, but say a few things about how to work on these things.
Wait, so this is also a conjecture that
That's equivalent to all the others. So that the map from the circle to the boundary of the Mandelbrot set is a homeomorphism. So this, by the way, is the same thing as the boundary of the Mandelbrot set is locally connected. And if the boundary is a continuous image of a circle, then it is locally connected. So that part is easy.
So it's continuous image, but it's not injective, right?
It's not injective, because 1/3 and 2/3 have the same image here. No, the boundary of the Mandelbrot, unfortunately, is not homeomorphic to a circle.
Yeah, I was just thinking at first, why doesn't it mean that they are homeomorphic, and then you said that it's continuous image, and I realized.
So it's very likely that the big conjecture is true, right?
It is becoming ever more true. By work of first Doody Hubbard, then Yokos, then Misha Lubitsch, and then Misha Lubitsch's various co-authors, including now Jeremy Kahn and Dima Dudko.
Yeah, so everybody is sure that it should be true.
That's their goal. That's their goal. If you find a counterexample, also,
Yeah,
it would save them a lot of time, yes.
Even if somebody just shows here are two components that are not separated.
Right.
Do you think if there was counterexample, how easy would it be to prove it?
It's like with Weierstrass, if there were a counterexample, it would have been found 100 years ago. What do you know? One thing I realized just recently, if there were a funny component like this, an interior component of the Mandelbrot set, that is not hyperbolic. And then you just do it's this big, you do a zoom in this thing, so that it would occupy half the screen, you would not see it. So here's the ideal picture, somewhere a bit of the Mandelbrot set, and this were a queer component. And now you do pixels like so, all this should be black, you would not see that. The problem is, take a parameter here, then the Julia set has no interior. So the Julia set is something like this. The critical point is here, and it hops around the Julia set. And now you have finite precision. So there will be some round of error you already see, it's a bit nearby. And so for all these points, you get almost the same Julia set. And some round of error will get you out of it. So you may have made the exact right experiments, you zoomed in, you got yourself a supercomputer, high resolution and everything. And you see something which unfortunately doesn't show what you were looking for, even though it was there.
You can expect it to be a little bit darker if you program it.
So there is what's called the hairiness conjecture by John Milner, proved by Misha Lubitsch, and apparently got inspired after some questions that I asked him. When there are certain points in the Mandelbrot set, for instance, the limit of the Feigenbaum doubling, then you zoom in like so in ever smaller zooms. Hairiness means that in the zooms, the Mandelbrot set fills the whole plane. Not necessarily in the sense of area, but so that if you have a big zoom here, then the Mandelbrot set is dense, or it's getting ever more dense as you zoom in. So things will get dark. In certain cases, yes, Misha Lubitsch. I don't remember which, yes. But it was a conjecture. In particular, I think it's the Feigenbaum point.
So the conjecture is that at each point, it is at each boundary point.
No, certainly not. There are certain many boundary. What is the meaning of many? Yeah, those that you find most easy. So when you take -2, for instance, then the limit is just an interval if you zoom in. And in many points, the limit as you zoom in equals the zoomed in Julia set at that same point.
But when you say limit, in what sense?
Hausdorff metric, if that means something to you. I'm a little bit, we can discuss a lot of things. So let's continue the class tomorrow at the railway station at whatever. But tomorrow is the seminar. I still was hoping to make a few more comments in some other direction. And now this can only be very sketchy, but it sort of give you some direction. So specifically, this one is the famous 315 and 415 for period 4. Those rays land together. How can we prove that they land together? These two parameter rays. So let's look at the dynamics. What I want to show is that not only do they land together, but for every parameter, Mandelbrot set or not between those 2 points in the Julia set, the two dynamic rays at angles 3/15 and 4/15, both at period 4, land together at the same point. Okay? So let's see what that means. And maybe I want to draw this lamination again. So somewhere there's the two angles of period 4. Suppose they land together. And you check, well, then the image is 6 and 8. The image is 12 and 16. 16 is 1, and 12 is -3. And then you get something 2 and -6. And let's see, the image 2 times 2 is 4. -6 times 2 is -12, which is 3. So that was a rough sketch. If we know that these things land together, this one among the full forward cycle is the shortest. The length here is 1/15. Here the length is 2/15. This is 4/15, and this is 4/15, and this is 8 or 7, whichever way. So this is the shortest. And then with a little, let me draw it a bit differently. I want to draw the two pre-images. If I take one of them, I get the diagonal. But I take the, like in this construction here. But I take two pre-images like so. Okay? So if these two rays land together, then we know their forward orbit, and we know the pre-image looks like this. The critical point is the point of symmetry at the center. And now you can check that the domain between these two angles, let me draw them a different color, map here. And in fact, the whole domain between those things will map there. This disk up to here maps biholomorphically up to this guy. And then this complement is symmetric, so it has the same image. So this part has to map 2 to 1 up there. You see that? So just out of the hypothesis that we have two such dynamic rays, we know that the critical value must be up here. And all this, by the way, I'm trying to recite. I was promising John Milner. And he said he read my PhD thesis. And not only did he read it, he said he was inspired by it. And in the preface to this paper, he writes, so this is inspired by the recent PhD thesis of Schleicher, which contains whatever interesting ideas and which is highly recommended. And that inspired him to produce this thing. So, yes, I was very proud of it. So you see that the critical value is between, so somewhere, if it's on the complement, its ray must be somewhere between 3/4 quarters and 315 and 415. So somehow the critical value must be somewhere, when it's outside at least of the Mandelbrot set, it must live somewhere here. Okay? And now, I want to go into the Julia set picture again. So we have the two rays, 3 and 4/15. The critical value could be outside or not. And now we change the parameter. It's true outside of the Mandelbrot set. And then everything will change, but the rays will change continuously. So the critical value is here, I move the parameter, the Julia set moves, the critical value moves, these two rays move. And how can it fail? For, like when you're here, you have that square, the two rays do not land together. And now which changes can those two rays break up? So question, when does 315, 415, of course I can generalize, it's just a special case, break up? They surround the critical value. And there are two possible cases. Either the two rays themselves break up, they cease to exist, or they no longer land at the same point. So how can a ray cease to break up? So the ray pairs, as the critical value moves over, the ray is periodic. By the time the ray comes on this ray or on that dynamic ray, then when you take pre-image of such a ray, here's the critical value, then the pre-image looks something like this, it breaks up. So one way of spoiling this is when the critical value is on such a ray. But you remember case 1, remember phi of C is phi index C. If the critical value has some particular coordinates, that's the coordinate of the Mandelbrot map. In other words, this ray breaks up if and only if in parameter space you are on this ray. And the other one breaks up if and only if you are on this ray. So that's the first case. So that means you're on the rays, on the parameter rays, the Mandelbrot rays, 315, 415. And the second possibility is the landing point is no longer repelling. If it's a repelling point, then you have some certain continuity, and then things go nicely. And now with some theory, you can show that means the two rays lands at a parabolic, which means rationally different point. And you have to analyze this a bit, and you check there are only countably many candidates. So you have a domain in the complex plane, in the Mandelbrot plane, which is bounded by two curves and countably many further points. And the only way for this collection to separate is if there's in fact one point that splits this off.
So the picture is like this?
Yes, yes. So that is an outline of a proof why any two such parameter rays must land at the same point, out of pretty much nothing. And I wonder why this has taken John Milner to observe this, and why he needed mathesis for this, but it's a true fact. I would like to add one more thing, and then I can go on forever, as you know, but then we have to find some other way. Let me add one more consequence of this. And now I erase here, and then we are ready for the party. I wanted to keep that one. So we have a bit of the Julia set, and we have the two rays, 315, 415. And well, let me draw on the disk again. We have here, this image is here. This is the two images, and then the two pre-images are here. Well, actually, one of them is this one. It's periodic. Maybe I didn't draw it. This one is already that. You see, this is period 4, so step 0, 1, 2, 3, and then here at 4 you're again. So I had one step too many. So I get the two symmetric ones, and I can, so 1, 2, 3, 4. The preimage of number 1, mod 4, is this one, but it's a pair. One preimage is periodic, the other is preimage. It's pre-periodic. I get an extra pre-periodic one around this, I get a pre-periodic one around this, I get a pre-periodic one around this. Which means somewhere in here, I have two pre-periodic angles, which is something over 15 times, taking 4 times preimages times 2 to the 4. And here the same thing, and you can compute which one this is. Okay. And now let me add a green line. So I take an equipotential curve. I'm outside the Julia set. Remember, we have the equipotentials in the dynamics. So there's an equipotential here, which has a preimage here, which is a preimage here, which is a preimage here. That means there's an equipotential curve in here. So, no, it's, so which one do I want to? It will be here and here. Because these two rays, like so, will come back after 4 steps to the same rays further out. So this connecting point goes there, and those 4 rays after 4 steps will also go here further out. So we have a domain, which is here, that after 4 iterations maps to this domain with degree 2. Okay? So we have a proper holomorphic map from some domain to a larger domain of degree 2. And after making this a polynomial-like map, remember that. So there's common boundaries, so I have to make it a bit thicker. So I take something a bit thicker like so, and make a little bubble like so, which is just technicality. But with this little thickening, that means for all, I just have used the 2 rays. Out of this, I always, for all the parameters inside, I get a polynomial-like map of degree 2. And now I have to check, is the corresponding Phil-Julia set of the polynomial-like map connected or is it not? And then, if it is, that gives me a little Mandelbrot set. Remember, the little Mandelbrot sets are coming out of little polynomial-like maps with connected Phil-Julia sets. And the proof that the Phil-Julia set is connected when the critical points don't escape is the same that I gave you earlier. Also works on this setting. So it turns out, if you look at this carefully, this is a way of constructing kind of the frame for the polynomial-like maps for all the parameters that you have inside. And now you ask, is the Julia set, the little Julia set, connected or not? That means, does the critical point leave the domain or not? When you're outside of the Mandelbrot set, it always leaves it. But in the Mandelbrot set, there should be a little Mandelbrot set within the big Mandelbrot set. Right? So how do you see this? If okay, safe. The little thing maps to the big thing, so there is a danger. If you happen to go, you can stay inside. Well, if you go out in this direction, you're outside of the Mandelbrot set. But you could be in this domain here. You could jump out of it, even though you're staying in the Mandelbrot set. Then the large Julia set is connected, the small one is not. And that implies here you have a little pair of rays. Let me draw it larger. You have a little ray pair. Somewhere inside you have the Mandelbrot set. No, it starts down here. Little Mandelbrot set goes on. There is a little ray pair that says, after one turn, this array can compute those angles. So if you chop off this thing, if you're up here, the filter set there is not connected. After the second turn, you get another one here and here, which you have to toss out. And there are many more dyadic angles. So in every iteration, you toss out something more. And what is not, if it doesn't escape through those, then it doesn't escape at all. That means the little Mandelbrot set in here is the big Mandelbrot set within this red region minus all these countable many small ones. So that way you can, just out of combinatorics, construct the little Mandelbrot set. Okay, so somebody wants to, okay, I think this is a nice conclusion. I hope you roughly get the idea. And if not, I can only recommend John Milner's paper, which is always fun to read. So, it's been a great pleasure to be with you here all the time. I enjoyed all the discussions, all your questions, and I hope we will meet again on whichever occasion. And I wish all the best to you personally and to KSE and to Ukraine as a whole. Thank you very much. Okay. Turn off. Done my work. You're a great audience. So this is approximately the expected ending time anyway. Does this make any sense?
I think it will.
Okay.
And like this, together with the book and some articles together, will make a lot more
Well,
sense.
that's the perfect expert. Yes. Oh, I want to take my jacket.
Some connection, like where goes like part of the boundary of any hyperbolic component to when we use by holomorphic phi where they go to what point, what part of boundary of this field.
So you want to find the external angles of points here in the... So let me give you a quick answer. So you have an implicit answer. So there's angle theta. You have theta over 2, theta over 2 plus 1/2. And then you compute 2, 4, and whatever the forward limit is. If it so happens that the orbit of theta stays always on this half, never goes here, then, of course, the partition depends on its own angle, its own plane. That's the case if and only if you're on the boundary here.